Name is Vaibhav, and in this video, I'll walk you through our project, uh, Google Local Business Rating Prediction. The goal of this project is to predict Google Local Business Star ratings from 1 to 5 using the text of user reviews plus a little bit of simple metadata like user ID and review length. In the notebook, this is the section uh, where we defined the problem as a regression task, where the input to the models are the review text, um, which is free form natural language, and simple metadata like user ID and review length in words, uh, which I later use as uh, features. The output is uh, a, a real valued rating between 1 and 5, which we can think of as a continuous approximation to the star rating. Even though the stars are ordinal, treating them as regression target um, lets us use standard models and squared error based losses. Um, I explain how I evaluate this regression task under the evaluation metrics uh, subheading, where we use mean square error, uh, which penalizes large mistakes, uh, root mean squared error, which puts the error back in star units. So if the RMSE is say 0.8, that means predictions are off by zero point 0.8 stars on average. And mean absolute error, which is the absolute difference in the stars. We also use R square, which is how much of the variance in rating is explained by the model compared to predicting the mean. Uh, the main numbers I report in the code are MSE and MAE and test sets, uh, but with extra matrix, it's clear why squared error is the main objective and MAE is the main interpretability metric. I also define uh, the baseline and the validity of the prediction. So we use two simple baselines: a global mean predictor, which always predicts the average training set rating, and a user mean predictor, which predicts the average rating each user has given the training data and falls back to the global mean for new users. These baselines give me a trivial baseline, which ignores all the features except the marginal distribution of ratings, and a user bias baseline that captures how generous or harsh each user is. Uh, so uh, here we import domain libraries um, and tools like Ridge and some standard utilities like gzip and default dict. I defined the two helper uh, functions MSE and MAE here too. Um, which implement the metrics that I described earlier, and the small utility readgz to stream one JSON review at a time from the compressed Google local dataset file. These helpers are reused in the modeling and evaluation sections, so I set them up right at the beginning. Uh, Here I explain where the data comes from. So we use Google local reviews 20 2018 data released by the course. It contains user reviews um, for local businesses with fields like ratings, review text, G plus user ID, G plus place ID. In cell 2, here I call readgz on review dot clean dot json dot gz and load up to 200,000 reviews. This uh, this is just to have to run it to make it computationally feasible. Um, and in this section, um, I convert the Python list of reviews and digs into pandas data frame called review df. In cell in this cell, I keep only the core columns that matter for this project, which is rating, review text, G plus user ID, and G plus place ID. This gives me a compact table focused on rating prediction task. The next in this next part, uh, I do three main things, which is drop rows with missing ratings or drop review text using dropnar, and uh, convert review text to strings, strip the white spaces, and remove any empty reviews. Um, Next, I create a simple metadata features called review length, which is just a number of words in each review. Review length serves as a basic proxy for how detailed a review is. Later, I'll add it as a numeric feature alongside TF IDF text features to see whether longer, more detailed reviews help predictions. Um, Now, here I do some quick EDA. So, I plot the distribution of ratings using histograms over the star values from 1 to 5. This shows the data is skewed towards the high ratings, which is typical for online reviews. Um, Most reviews are relatively short with long tail, uh, very long tail for the detailed reviews. Uh, this EDA motivates the modeling decisions because ratings are skewed. A naive global mean baseline will already be biased towards positive rating. Now I explain how I split the data. So I fixed the random seed to 0 for reproducibility, randomly shuffle all the indices and then split them into 60, 20, 20, 60 for train, 20 for validation, and 20 for test. The training set is used to fit the models. The validation set is used to compare the baselines and pick modeling choices. And the test set is kept completely held out until the end for evaluating. And this helps uh, keep the numbers not optimistically biased. So now there are four different uh, models. So here in baseline one, I implement the simplest possible model. So I compute the average rating on training set, which is my global mean. Then I predict the same value for each example uh, in train, validation, and test, and then compute MSE, MAE for this each plate. This gives me a lower bound on performance. Any reasonable model should do better than always predicting the mean, especially on the validation and test set. For this, for the second baseline, I made a slightly smarter uh, baseline that incorporates user bias. So, um, after building a dictionary user rating on the training set that maps each G plus user ID to the list of ratings they give, we can compute a user specific mean rating for each user. and then define the predict uh, user mean that each that uses the user's own mean if they're present in the training dictionary. It falls back to the global mean for unseen users. And then I compute the MSE and MAE on train validation and test. This baseline partially adjusts for harsh versus generous data, and it's also a good sanity check for um, overfitting. On the training set, users can look very strong because we're literally summarizing the labels. But on the validation set, if they don't generalize, that tells us that we cannot rely solely on user bias. Um, After the baselines, uh, we moved to the first learning model. Uh, Here I extract the raw review text from each, then split into train text, validation text, and test text. Then I build a vectorizer with uh, this range and uh, and fix this TF EDF model on the training text and transform all splits to get a large sparse matrices X train, X val, and X test. On top of these TF IDF features, I fit a rich regression model with uh, alpha equals to 1, which is essentially a linear regression with L2 regularization, which handles high dimensional sparse features well and controls overfitting by shrinking coefficients. And it is fast for this dataset. After training, I compute predictions on all splits and report MSE and MAE. This text-only model is my main model and the key comparison point for baselines. Um, Now for this model, I test whether a simple numeric metadata can improve performance beyond text alone. In this cell, I compute a user mean feature from the training that's data similar to the second baseline, extract review date length for each example, and combine it with the uh, user mean into a two-dimensional vector. Um, Review length user mean from train. And then I standardize these metadata features using standard scalar so they're comparable. And then I concatenate the scaled metadata matrix into to the TF IDF matrix, producing a, a full X train, X val, and X test full. Then I fit another ridge regression model on these combined features and compute MSE and MAE again. This model tests the hypothesis. Can we do better uh, by giving the model both the language and a couple of cheap metadata signals? Um, so here is where we can answer that question. So uh, here I summarized all models in a single table. Um, the columns train MSE, val MSE, test MSE, val MAE, test ME, readings across the table. The global mean baseline has MSE around 1.6 and MAE around 1.0 on all splits. Um, the user mean baseline has very low training, but much worse validation and test MSE. This is just overfitting. Uh, and uh, just overfitting on the user IDs. It memorizes their averages, but it doesn't generalize well. The text only TF, IDF, Ridge model improve this performance. MSC drops to 0.77, MAE to 0.68, which means predictions are on average less than a star off. It This clearly outperforms both global mean and user baselines. Um, the TF IDF plus metadata model doesn't look that good and a little suspicious because it has a very low training MSE, but worse um, validation slash test MSE and ME. And this indicates that it's overfitting when we add both review length and user mean in, into the same linear model. So in terms of generalization, the best model is the text only TF IDF plus Ridge. The metadata model appears more powerful on the training data, but fails to carry that performance to unseen reviews. Um, in terms of metrics, the combination of MSE, MAE, and R square gives a clear picture. MSE is directly aligned with the loss used to fit the ridge models. R square, if computed, would tell us how far we are from the variance of the rating distribution and how much additional explanation we get from the features compared to the global mean. I also do validity check by comparing each model to the global mean and the validation test, not just on train, checking whether the model that looks good on train also does well on validation and test. The fact that TF-IDF plus Ridge beats both baselines and maintains similar performance across validation and test guarantees that the model has captured um, the signal from review language and we're not simply overfitting. Finally, in in this part of the notebook, uh, I summarized the main findings. Very simple baselines like global mean and user mean perform poorly on validation and test, with MSE around 1.6 to 1.7. A text only a TF IDF plus ridge model substantially improves. Um, adding the extra metadata features that we tried actually hurts generalization, even though they make training error look great. That suggests that most of the information for this setup is already encoded in the bag of words representation, and uh, naive metadata addition can only encourage overfitting. This aligns with a lot of related work on review-based rating prediction. Um, the traditional approach uses these kind of models with linear and factorization machines to predict rating for reviews. But more recent work explores deep learning like CNN and RNNs, or even transformers over text, sometimes combined with user and item embeddings from collaborative filtering. Many papers that Many papers also find that text alone can be very strong for predicting ratings or ranking items, especially when there's enough labeled review data. Uh, our project sits in that space, but focuses on an interpretable uh, baseline. It shows that even without deep models, a well-tuned TF-IDF plus rich pipeline can beat naive baselines by a large margin. It also highlights that not all metadata is important. Adding user means uh, directly into linear model can lead to overfitting instead of improvement. There's several interesting extensions um, and future directions, like adding a business level feature to separate place or category, um, trying an un trying a regularized model that separates user and text effects more carefully, or replacing TF-IDF with pre-trained embedding or even transformer models to see how much performance improves relative to this strong linear baseline. Uh, Overall, this shows that review language is the dominant factor for rating prediction in this setting, and that a simple, well-designed linear model can do very well. Uh, this concludes my walkthrough of the project. Thank you for watching.